Okay, let's get started with today's recitation. Welcome to Recitation 4. Today we're going to be going over hyperparameter tuning. It's sort of a continuation to Recitation 4 with more, Recitation 2, sorry, with more context as to why you're doing certain things and how do you decide between different hyperparameters. And hopefully this will help you across for not just your homework 1, P2, but we tried to make it as general as we could so that it would help across all of your further pathways as well. So does anyone remember what we covered in recitation 2? Anyone? Okay, so we spoke about some common data pre-processing techniques. How can you perform your ablations? How can you change model architecture, weight initialization techniques, some different optimizers that you could use. More importantly, we covered certain hyperparameters that you could tune, like the learning rate and dropout, and how to make all of this sort of come together for the homework 1 part 2. Today, we're going to be diving a little bit deeper into certain other normalization techniques that you can use. Um, why are you using learning rate schedulers? What are some different types that you could use? We'll also talk about grid and random search. How do you use 1DB amongst your study groups? How do you perform ablations effectively? And how to work in your study teams across all of your part 2. So this will not be very specific to 1P2, but you should be able to apply it to 1P2 as well. But more importantly, you should be able to apply it across most different pathways. So if we talk about normalization methods, we first need to think about why we need normalization. And we did cover this both in class and in the past recitations. But to give like a quick overview, when you have a neural network, you're going to be passing inputs to every layer. And when you have different batches, the distribution of your input changes just so ever slightly. So it's not very constant whenever you pass different batches. And so in order to account for this, we do what is called normalization so that your weights don't explode, so that you can optimize your network and it converges better. And there are really different ways that you can do normalizations. You've looked at batch norm and hopefully implemented that in your homework and used it in your homework 1 part 2 as well. But there are different other normalization methods you could use, like layer norm and weight norm, and all of these pretty much do functionally the same thing, which is normalize, but they do it at different dimensions, and we'll see how. So we've linked a lot of these papers, and I strongly recommend going through them when you decide to try and test either one of them for your future homeworks, just so that you know what is happening behind simply doing torch.nn.batch norm 1D or layer norm, or whatever it is that you decide to do. So like I said, we did cover this last recitation, and we mainly do normalization because we want to ensure that we are taking care of any change in distributions that happens across. So we try to minimalize or eliminate whatever internal covariate shift that you have. And you have different types of batch norm. You have batch norm 1D and 2D, and it really depends on the type of, the dimension of the underlying data that you have to decide what version you want to use. So there are a couple of problems that batch norm has. So if you have very small batch sizes, it's typically not very efficient to use. But more importantly, when you have sequential inputs, like in the case of LSTMs or RNNs, which you'll be studying in homework 3 about, it's not necessarily the most efficient way to have a running mean and running variance being computed. It can get computationally extensive. In which case we use layer norm. And how this differs from batch norm is in batch norm, you compute the mean and variance across each feature in your batch, right? In the layer norm, you look at each input within the batch. So you compute the normalization, the mean and the standard variations across all features for every input, so for every item in the batch. So like I said, it's the dimension that you're computing the normalization that differs. So there are other techniques like we spoke about earlier. So in the case of weight norm, you're going to be normalizing the weights of each layer. In the case of group norm, you're going to do it for a mini batch rather than all of the items in the batch. And you have instance norm, group-wise layer norm, and so on. But the important question is, how do you know what to use when? So a lot of this is definitely problem specific, but more importantly, it is also data specific. So if you, for example, find a certain problem or a use case, and they're using layer norm, and you're doing pretty much the exact same thing, it's entirely possible that layer norm is not going to work for you solely because the data that you're using is different, in which case you might have to shift to batch norm instead. So the way to sort of identify what works best is, of course, you need to experiment, but you also really need to understand your underlying input data distribution, what is the problem you're solving, and which of these sort of align with that. This is a very high-level overview of the different normalization techniques. The papers do have them in more detail, so I would definitely recommend going through them and sort of understanding what's happening in the back end. So let's talk about schedulers. A very common thing that hopefully all of you have used in your homework 1 part 2 is a learning rate scheduler. So today we're going to talk about a couple of different types of learning rate schedulers and how do you really decide when to use what. So the learning rate itself is a step size, right? So it helps you adjust your weights as you do backprop. So it becomes very important in knowing when do you have to decay your learning rate, when do you have to lessen your step size, because like we saw in the lecture, if you choose a very large learning rate initially, your models are going to diverge. But if it's too small, it's going to take forever to converge. And hopefully you guys are seeing this in the current homework that you're doing as well, where it just takes so many epochs to even get from 84.6 to 84.8 when your learning rates are in the range of 10 e power minus 5 or whatever very low learning rate you have. So a scheduler typically helps you do this. You don't have to decay your learning rate manually. It helps you decay it according to some function, and PyTorch offers different types of learning rate schedulers for you to experiment. We'll be covering some of them. A lot of them sort of derive from the others with very minor changes. So the step LR, pretty much what it says, it's going to hold the learning rate at a particular value for the number of steps that you give, and then decay it by whatever is the gamma or the rate that you've provided. So the step size here is 4, which is why you see after 4 epochs, it reduces by a certain amount, and then this continues until it goes to a very low learning rate value. So in case of multi-step LR, again, it's very similar to the step LR, except here you provide what are known as milestones or epochs. And it's only after those many epochs that your learning rate is going to decay. So it doesn't happen at every equal interval like in the case of step LR, but instead it's going to happen at these epochs, and you can pretty much set this to whatever you want to. But would you want to randomly choose milestones? Does anyone have any thoughts on how do you come up with milestones? How do you know which epoch you're supposed to decay your learning rate? Yeah?
Would it be based on like the validation accuracy or loss just once that starts to plateau or not change as much?
Precisely. So that's what you have the whole experimentation on 1DB for, right? So you go, you perform certain runs, maybe you use some other learning rate scheduler. You're seeing at that across all your models, there are certain epochs when your model is starting to saturate. Those are the epochs when you need to decide, okay, do I decay it? How much do I decay it for? And if you've run so many experiments where you know for sure that these are the epochs where I know my model is saturating, it's not improving, and I need to reduce my learning rate, this would be a good scheduler to use because you know the exact epochs from your graphs, and you can test out if your hypothesis is right that on reducing the learning rate at this epoch, my model is not saturating and it's actually learning and training better. So another very common learning rate scheduler you'd use is the exponential LR. The main difference is it follows the exponential decay plot, as you can see here, and sort of decays your learning rate to match this particular distribution. If by default your gamma is zero point 0.5, like in all the other cases, you get to decide how much you want to decay it by. A common rule of thumb is, again, you just experiment and figure out, but don't decay it by a lot, but don't decay it by very less either. So zero point 0.2 or zero point 0.3 might be a good place to start off with, so that you sort of figure out, okay, as I decay it little by little, how is my model accuracy changing? Or if you're tracking loss, how is my loss changing? And depending on that, you get to play around with gamma after you've done quite a few ablations. So another very common learning rate schedulers that a lot of you would have tried for homework one is the cosine annealing learning rate. Similar to the exponential LR, the difference here is you're going to be using a cosine function, which means it's going to decrease just ever so slightly across your different Tmax, or the different time steps that you have. So you might not see a huge difference between, say, these two epochs, but as you see the learning rate starting to decrease a little bit across different time steps, you'll get to really see what is the effect of this decreasing learning rate on your loss or your accuracy. But keep in mind that you do have the time steps for which you have to tune, or the amount of time that you have this running for. So it actually turns out to be a very important parameter. Again, so in case of different learning rate schedulers, you're going to have different hyperparameters to tune. This becomes one such hyperparameter. Another very common learning rate scheduler that you would have tried is the reduce LR on plateau. Uh, you can't show it on a graph here because it depends on the patients that you've set, and you know how much you're decaying it by. But how it typically works is, if you set patients to 4, for example, then it would work like your step LR, where after 4 epochs, it decays. So what exactly is the difference then between step LR and reduce LR on plateau? The difference is, in the case of reduce LR, you have a step that happens only when a particular parameter plateaus. In case of step LR, it doesn't really care about that. It steps down irrespective of what is happening, it steps down by a certain amount. But in case of reduce LR on plateau, let's say you're stepping down with respect to validation accuracy, which is hopefully what you guys are doing for homework one as well. So when your validation accuracy plateaus, when it's not increasing across 4 epochs, which was our patients, that is when it will decay, or that's when it's going to reduce. So using that becomes slightly more easier for you, because you don't have to manually change things, yes. And like in step LR, you're not going to decrease it no matter what. You're only decreasing it on saturation. When you know it's not converging anymore, then the scheduler takes care of reducing or decaying your learning rate at a particular epoch. So that would definitely be a good scheduler to try out with across your homeworks. But of course, again, coming to what do you use, how do you decide, it really depends on your problem. It really depends on the optimizers you're using, your network. It is possible that for the same problem, for the same data, two different networks can use different optimizers and different schedulers. And that's where you sort of make use of your study groups and try to figure out what really works best for this particular network, for this particular data, and things like that. So we did talk about different hyperparameters that exist in schedulers, but there are different hyperparameters across as well. So we'll be covering certain techniques that you can use for hyperparameter tuning, and Jill will be talking about.
Um, okay. Okay, is the mic working fine? Cool. So hopefully you guys should have started running ablations in your study groups, and hopefully you're doing well there. Okay, I see a couple of shakes. So then I think this is not a wrong time to start with that. So as you might have noticed, like if you are doing it alone, you would have had a lot of choices in parameters and a lot of range to try it with. So how would you optimize this process? Um, so obviously you can do it on your own, and obviously you can sort of figure out what you want to try it amongst your study groups. But then there could be a better way, right? For example, grid search here is something that you can use to try a range of values for multiple parameters. So for example, say you want to try like your learning rate with the number of batch size, for example. So if you have certain values you want to try for the learning rate and certain values that you want to try for your batch size, you can sort of just give a range, and then your grid search algorithm is just going to search for each and every value in that particular range. And so the crosses over here on this particular plot shows you what values are you going to use. So this, for example, would be something like point 0.19 and point 0, point 1. I mean, not point 1, but okay, you get the point, right? So for each of these values, you will be trying, you'll be running your training. So here, over here, if you see the blue and the red lines, imagine that to be your learning. So for example, say that we consider that the blue part is where your minima is lying. So you can see, you can sort of visualize it going inside of this graph, and the red side coming out, red lines coming outside. And so you can visualize that probably this is like a local minima and this is like a global minima. So if you see, if you're trying each and every value on this graph, is it useful? So what do you think would be the problem with this kind of method that you are using?
Too many combinations.
Right. You waste a lot of time. You have too many combinations, and what would you end up doing? All of these, for example, if you try all these values, you're not even reaching your global minima, and you might get stuck in local minima. Or if you were over here, you're just doing the opposite, correct? And you do not want to lose the precious compute that we have. You don't want to create a lot of GCP accounts. And so, can someone like come up with a method to bottle down on this?
Use random points.
Correct. Yeah. So one of the methods that we can do is we can choose random points. So that is what I was coming to. And so we have a random grid search. In this, we sort of fix like a distribution, and we give the range of values over here, and we pick random points now. So instead of going through each and every point in our grid, we are now looking at only these randomly generated numbers. And so you can see like we have reduced the number of combinations by some factor. Now, if you see over here, we have some points. Over here, we have a majority of points where we don't want it to be. And then we have a few points near the global minima. And then we have a couple of them near the local minima. So if you have run ablations even like individually, do you think that trying a couple of values once, like one iteration of it is going to help you? So how would you go about it? Like, for example, by intuition, like if you are just running a couple of values for your parameters, and then eventually what your mind does is it sees, right? Okay, where am I getting a better accuracy? Where am I getting a lower loss? And then based on that, if you see, okay, my learning rate is around zero point 0.3, that is too high for me. Or if I have a learning rate of say 0.001, which is very standard, you might see that your accuracy is increasing, or at least that your model is like stabilizing at that point. So you might want to try more values around that area, right? So in this particular one, I mean, think of it as one iteration. So then you would have to further search for values amongst your combinations to further look for what to search for in the next iteration. And so this is what we as TAs also did for our ablations. And this is what comes very intuitively. So for example, over here now, do you have any methods where you could use for bottling down onto these parameters here? What values could you use? Like what does your mind think? Like the most natural thing that comes to you? On range on what basis? Accuracy? Like if you see that, if you, for example, have the value, you have trained your model at each of these values where the cross is, right? And you have the value of accuracy that you get over here, say validation accuracy, then you know that some of these points are performing better than the others, right? The most intuitive one would be just, let's just take a threshold. Like if my validation accuracy is above a certain value, I just want to try with those points next, right? That is one of the values. But do you see, I see some very confused faces. So I think that you already understood that this would not be a very good idea. Why? Okay, so say this is your local minima, this is your global minima, okay, and you see that the loss is decreasing and your validation accuracy is increasing, but you have not yet reached that part where you know what is the correct validation accuracy. What if you set a lower threshold, and according to that threshold you have like more points near your local minima, and you end up bottling down on those points, and then even if you find more points around that area, you're still gonna be stuck, right? Another method could be that you take all the points above certain threshold and then find combinations of them. Say like an average, or like just add up, or say if you, I mean, this is a very specific scenario, but like what you want to get to. So for example, you have 2 points over here near your global minima, and somehow you're able to get to a threshold which gives you all of these points. You might want to try finding the nearest points and find like the midpoint of those points, which gives you a higher accuracy. Difficult? Difficult to figure out, right? So we are not yet here. So one thing you can think of is that you are actually using your validation accuracy as a sort of weight for these points, right? So one thing that you could do is resample from these points based on the weight, and that is what we call weighted resampling. So there are various methods for it, and I won't go into a lot of depth, but there is one simple method called particle filter. And what that method does is that from the distribution that you already have, it will pick out points for you based on the weight that point is associated with. So let's see if I can draw it. Can we get this up? I think it's here. Okay, once this comes out. Okay, so I'm just going to draw like, say this is the distribution of points that you have got. Okay, so what I mean by this distribution is that say these are like your validation accuracies, and this is what you've got. These are your points. So let's assume there are like more points in this area because this curve is like up here, and then you have some more scattered points here, and then some points here, and so on. Now, what a normal resampling would do is that it sees more distribution, more points in this particular area, because you see that it is more closer, and it'll try to pick points from here, right? But are we sure that these points are giving us the greatest validation accuracy? This particular region could be all of the blue area here. Like there could be more points in this area, and that is the only reason why we see more points generated there, right? I mean, there's no fixed point for us to actually get these points because we are randomizing this process. There could be more points in this area. But what we could do is we could attach their weights to it, which could be the validation accuracy, and based on this weight, the model will figure out how to pick out points which are better for us. And so you can sort of think of it as cloning these points again. So if you're associating a greater, so for example, a point over here has validation accuracy 0.5, and a point over here has validation accuracy 0.8, it might just create one more instance of that point here. So there's like a greater probability of it getting picked up. So that is something you could try. Although not everything needs to be automated, we might get an intuition of what is working better for us and what is not working better for us, and we can figure out based on that as well. For example, like if you have tried different architectures by now, you would know that what role a dropout plays in your architecture. So if you are like making the architecture very deep and very wide, so I hope like you know what dropout does. From one layer to another, it's sort of blanking out some values, some neurons, so it does not pass that information forward. So you probably want to keep the dropout rate high when you're wide, when the model is like wide, or when you're going like deeper. When if your width is too low and you're setting the dropout value to be very high, that doesn't really make a lot of sense, right? Because you're anyway bottling down. So you might not want to keep it high. So based on like your real life experience and this, you can also set this the second iteration on your own. So you don't have to specifically resample or anything, but there's just like some ways to think about it. Any questions? So one good way to do it is OneDB. It was a part of the Recitation 0 P Part 2 recitation on OneDB. I'm not sure if you have gone through it. If not, now could be a good time. It is a useful thing that you could use for ablations. So Colab Notebook and the video is linked in this slide, and you'll get the slide, so you can go through it. But I'll just take you through it like I'll just give you an overview. So here, so basically what we decided right now, right? For each of your hyperparameters, you set like a range, and you want to randomly pick points from that, and you want to run these ablations, right? So WarnDB actually gives you that opportunity to just set your range and decide how you want it to be. So over here, like you have the sweep config right there, and the method is random. You can also keep it something else. So you get more information about this in the recitation, and the OneDB link is also shared. So you might be able to find it there, but you can also send it. You can also set it to like direct values. For example, over here for optimization. I'm sorry. For example, over here, for the optimizer values, you have SGD and Adam, right? You could also set it to something like, I want it from a Q-log uniform value distribution, or I want a uniform distribution. Or you could also set it to like incremental values that starts from 512 to 1024, and then like you just keep on adding, which will be helpful for a batch size. So you can actually just make this parameter dict and then specify the range, and then it'll do the sweep for you. So that is something that is interesting. And I can show you how it looks like. So these sort of insights are really helpful. So for example, here I've just plotted like the learning rate and optimizer and the batch size. And this sort of gives you like an idea of what is actually helping you. So if you see over here, the loss is the least with this color. And so we see that we're getting these good values for both the optimizers. So maybe switching the optimizer is not that helpful. But again, like you would see that some optimizers would require a higher learning rate than the others. So that is useful for your ablations, right? You would want to like set your ablation patterns in such ways that you want to try Adam with lower learning rates, and you want to try SGD with probably higher, and so. So OneDB sort of, after you have given the range, you specify how many runs you want to make, and here it's like 50 runs I've specified, it runs it for you. So this could be a good way of automating this process. Okay.
Quick question.
Mm-hmm.
So like in the charts, you have kind of like two hyperparameter search space. Like in reality, there are many more.
You can add more.
Right, but like so 50 runs is that will look
No.
pretty sparse in terms of the like
You're right.
X's, right?
Yes.
So like, what's a sufficient number to run?
That will depend on the stage you are at. Like if it is your first iteration or your second iteration. Also, you could limit the number of epochs and like run for more time, or you could limit your data size and run for more time. It completely depends. But yes, like I've just run it for 50 epochs to get this fancy graph so I can explain what it looks like. You would want to run it for larger runs, but the point is that you are able to automate it now. You don't have to like explicitly think what values you have. So sort of a way to randomize it.
Mhm. I get, like, when you run these, it's, that sounds like, even though it is more efficient than just doing grid search, it's gonna take a lot of time. Like,
Right.
would you block out like 2, 3 days just to let this run? Like, it seems like it might be kind of crazy.
Yeah, that's a good question. And I would say like it's like a trade-off. But what I would do is I would run the sweep and think of another architecture to implement and get that code ready by that time. That would be a good way to efficiently do it. So in P2, for example, you will be working with different blocks from the famous architectures like connext, resnet, blah, blah. So you'll have to learn how to implement those residual connections, those blocks and everything. So one thing would be like just implement a block, run the sweep, work with your group further, and you'll be getting insights anyway, like continuously. So if you feel like it's not working, you can just stop it at that point and you can try. So yeah, all this is like you have a method to do it. I won't say it's good all the time, but just a tool.
And typically, you wouldn't add like 10 different values of learning rate, 50 different values of
Right,
you might have a lot of parameters, but you ideally want to test like 4 or 5 values of each of
right.
them. Don't test everything at once because also getting insights becomes extremely difficult. Of course, you can look through patterns,
Mm.
but there's only so much of it you can do. Some of it will come from intuition, and you need to start somewhere, but don't start with really long lists of them.
Yeah, so this is with the assumption that you have some particular idea of, by now, like you've worked with MLPs and for your homework one, right? You would have some idea about what optimizer goes with what learning rate combination or so on. So you don't want to ideally put like outliers. Like if you know it's not going to work, don't put it there, right? So yeah, maybe for your first iteration, you need to take like less values, maybe distant values, and then get closer on that range for the value that works better. Okay, so I know like we just got the study groups, and I don't know how many of you are actually like discussing amongst yourselves and everything. If you think that running ablations on your own is going to give you a higher accuracy and will make you get up the Kaggle competition scoreboard, this is not the course for that. Like yeah, you need to be ambitious and try to achieve those high cutoffs, but think of it in a way that if you do it with your study group, it's going to be much more efficient because you have like 4 people working on it. So in the time that you could have run one ablation, there are like 4 people doing it. Contact each other, contact your mentors, contact um, like any other TA, whoever you can think of, and so on. So like just a reminder that you have study groups now, so you have extra set of hands to work with, and you should definitely consider that. And so yes, OneDB in that way is good because you can create like your study group and add members over there, and so you'll be able to see all their applications together and be able to compare, and so you would know what works best. So you would ideally eliminate all those extra runs that you're doing just to figure out what is good when the other person has already done that, right? So that is the thing. Another thing is that how do you interpret these graphs? So in the office hours, like we've noticed that a lot of you have just ignored the OneDB bit, and you think it's not necessary because you already get the logs in your console saying what is the validation accuracy, and you feel like you can track the progress there. For one run, sure, but then if you want to run evaluations, like you need to have these values to compare, and also these sort of graphs is not something that your mind will create on its own. So if you have OneDB and you see a graph like that, does anyone know what it means? If I have these variations, I'm telling you, like this is the validation accuracy graph with respect to epochs. So now, what do you think do these variations mean in the graph?
Probably like using a high learning rate and also getting low.
Right. So, so you get such kind of insights. So, for example, over here, as she said, the learning rate could be too high. Other thing is that you might want to regularize it better. If you want to use a higher learning rate, you might want to change your optimizer and see if that is working for you, right? So this is the kind of thing, and also you get to know when your model is actually starting to plateau. So what in your logs, what you see is that, okay, my learning rate is just increasing by some point 0.01%. I would say that is a good thing if your model hasn't started plateauing yet, if it hasn't converged yet. It is still increasing, right? So, for example, the green line over here, it is flat. Like that is something you can say that, okay, it is plateauing. But again, if you see like this one, it's still increasing, right? At this point is where I mean, you don't need to give up on that model yet. And these are the kind of things you'd only know if you go through these graphs to figure it out, right? And so this is where all the schedulers and everything come into picture. So say you are at okay, let's just say you are at some point where your accuracy is still increasing a little bit, but you don't know whether you should go ahead with that or not. What could be the possible solutions to that? Say your learning rate is like really low. You have been using step LR and you have reached some 0.0001 learning rate. What would you do? You would ideally, if you just look at your logs and your current implementation, you would just give up. But if you have this graph and you see that it still has the potential to increase, what you could do is use warm up with cosine annealing, which increases your LR for a bit, and then it sort of follows the graph. So there is a possibility.
When you're doing that and you've already pre-train something and then save that into one DB, when you like pick that model back up and you change the scheduler there.
Yes.
Oh, okay.
Yes. So you can basically change anything in your except your model architecture. So for example, what we also suggest is that if you have, say, a 7-layer architecture, but you have fixed like a dropout rate of zero point 0.3, trained it, reached 85 accuracy, and then you see that your model is not learning anymore. What you can still do is change the probability value of dropout. It doesn't change your architecture, right? If you if you reduce the dropout by some amount, it might lead to your model learning a little more. And so what you could do is train it for some time till like 20, 30 epochs. If you see there's no progress, you could just reduce the dropout and then again train it again. So you can change, yes.
Yeah, so if we do that strategy, do we need to keep track of what we're doing to submit at the end or something? Like for
Yes,
change? Oh, okay.
yes. You'll have to basically keep track of everything. And so you need, if you have one DB, you'll sort of know, yes.
Oh, no, sorry. For this, like, at times, I think it's helpful to train on like subsets of the data, right? Just to do it quickly. So how would you recommend um, the interval that you log at? Like, would you do it at, like by the examples your model is seeing, just to make sure that, because if two of these models, one of them was trained on all of the data,
Right.
and
So,
one's not, then yeah, like number of epochs is less.
right. So you just do like a 1 dB log. You add like a dict, right? You just put a parameter saying um, batch, I'm sorry, number of records or like whatever your subset is. Yeah, and then in 1 dB, like you can actually filter down. So you can filter on your records that have been run with that particular batch of records, and so you'll only be able to see graphs relating to that then. So it's actually nice. Okay, this is a live graph, okay, and see, you can actually get a lot of insight, like who has run with what parameters and everything. And so like you can get a lot of idea based on that, and you have like runs and you can filter down on what kind of runs you want to see and see graphs only for that. So you can interpret. I think that is it. Any other questions?
Would you recommend logging it every step or like every epoch or doing?
For 1 DB?
Yeah,
Ideally every epoch.
because this kind of variation that you spoke about, this probably means that like 100 epochs were on.
Yeah.
Okay.
So, what do you mean by each step?
As in each backprop step.
Oh, no, like you should ideally track every epoch. Yeah, like at every epoch you would have different values for test accuracy. Like what would you compare at every step? Like the gradient?
No, to like just track it on one because I mean I was just asking because this graph looks like there's been 100 entries, so was it 100 epochs stuff like that?
Yeah. So, and like a general thing in office hours, people said that, okay, we run it for 10 epochs and then the accuracy is increasing by just 0.1. What to do? So homework too, you'll have to run a lot more epochs, so be patient. Like don't get overwhelmed by the number of epochs you need to run.
There, like, it seems like experimentation is really like figure out what's best, but like, why is there no good intuition? Like, trying to figure out, is it just like the lost service that you're trying to find your way to? Or like jagged and complicated as it gets deeper, essentially, and so there's no point.
Okay, I think you should answer that question for me. If I have two different, okay, I am analyzing a data set which has images of different animals, and I have a data set which has words. Like, how are those features generated? Like, how would you know where the minima is? Even if it is like a data set of animals, but there are two different data sets, how do you know where the minima is? Like every data is different, right? So even if, yeah, um, even if you add just one more extra feature, or you just change the dimensions of the image, like your values are ideally changing and you want to reach the minima. So yeah, but again, like it is randomized, it is a lot of work, and that's why like there are so many ways to run aberrations and track aberrations. But you should be able to get a better idea. Like I said, like for the dropout, like you'll figure out that if the width is too less, like making the dropout more is not going to work. You would probably figure out that with Adam W, higher learning rate is not going to work. So you will, so that's what you're learning. Like if everything is randomized, then we don't have any intuition, and that's not what we want. But also based on how they work, like if you read about it, you'll figure out like what it's actually using. So like a normal example would be, say you're using the step LR, okay, so you know that it's going to reduce your learning rate. So you would want to start with a higher learning rate, right? With exponential LR, you know that it's going to decrease it very much. So then you want to probably use a higher rate for that as compared to cosine annealing that starts from like less. And then also like there are a lot of ways. Even for the schedulers, you have cosine annealing with warm up, and you can also specify, like, because the cosine graph, it goes like up and down. So if you see, like, maybe after this iteration, if your model is already very close to your minima, you don't want your learning rate to like shoot up all the way there. It might make it diverge. So there is a value you can set that will only make it like increase till here and then go back. Again, like this is very sudden increase in the learning rate. You have it with warm up, then your graph will look like something like that. So it's slowly increasing, then decreasing. So like you have ways to do that, but again, like you have to run the evolution. Like there's no. You have anything to add?
Just to add on to that, what she said, right? There are so many moving parts in every homework. Just consider homework one, part two, and just look at the architecture. I can play around with width, I can play around with depth, I can play around with what activations I can use. Where do I put batch now? Do I put it after linear layer? Do I put it after the activation? Do I put it before dropout? What is the dropout value? There are so many things in just one cell of code that you can change. And we are talking about schedulers and optimizers, which on their own have like 20 different types you can use. Each of them have so many hyperparameters. So when you come to us during office hours and say, hey, I'm using this, I'm doing this, it's pretty much a learning for us too. Okay, you're doing this, you're getting this, because it's very probable that we also have not tried those combinations, because there's just so many combinations that you can have. So is there a sure short way of knowing what works? I don't think so. But that's probably why you use these things, figure out your ablation sheet, who does what, and then you get those insights. That's pretty much the only way.
Yeah, with time you just like figure out and make your range of
Yeah.
trying parameters a little narrower. But other than that, like there's no. And I think like with time you'll get to know like is making your network deeper helping you, or is it making wider helping you, or none of them is helping you. You just need to work with other parameters. So
And so maybe like a good workflow would be when the homework comes out, brainstorm with your TA over a set of architectures to start with, to start the iterations. And then once you kind of start to get a sense of what's good there, then you can go into the hyperparameter.
right. So yeah. So I don't know what you mean by brainstorm, but if you want to understand what each architecture block does, what it's likely to learn, maybe. But again, like there is no certain way. Like we are using CNNs for language also now. Like so,
Yeah, yeah.
yeah. Like
So
you
I guess
still,
saying like, here's what we're thinking of running on.
yeah.
Is there anything glaring that we're missing? Like, and then they can say, oh, maybe think about this, and you can maybe add that in.
Yeah, I mean, ideally, I would say that brainstorm with your TAs about what each block means, what it's trying to do, and then you'll still have to run ablations. Like maybe after one iteration of ablations, your TA would be able to help in figuring out what you should do next. But yeah,
Just one question. When we released the medium cutoff architecture, how many of you tried the exact same architecture? Were you able to pass it at one shot? Were you able to cross? No, you weren't able to, right? Like there were still things that you had to do in order to cross. So even if you sit with your TA and we tell you, hey, you know what, use this, we're not going to tell you everything else. Like it's still left up to you to figure out the million other things that you have.
yeah. I mean, ideally, like we have done these, we could just tell you what to do, but then what is the learning, right? So yeah. I think this is it we have for today. Like, is there some? I would like to get some feedback. Like, do you want us to add anything to the recitations? You feel like you're lagging behind with something that you don't. Yes.
I feel like this one was really helpful to see like the different schedulers and everything. I really like this one.
Yeah. Okay. Thanks.
I
Yeah.
guess just some like, if you guys could like give tips, like just in all recitations, like tips on how to train and like the best practices and other like heuristics that might be useful when we try to like train our models, I think that'd be helpful.
Like yeah. So we have boot camps, and that sort of gets you started with the homework, and then hackathon is the time. Like, eat your TA's heads. Like I am a TA, I don't want to have my head to be eaten up, but yeah, that's what like normal tips. Actually there are very few generalized tips that we can give, and so we are stressing so much on logging and interpreting graphs so that you are able to get those insights on your own, because we will also be doing that. Like we will also be looking at your graphs and everything and try to tell you like what you need to work on. So yeah, but if you feel like you're getting confused with, for example, a lot of people in the office hours came up with the fact that they did not know what scheduler to use and they did not know what's the difference. So then we included that. So if you ever feel like you want something, then just piazza, email, anything works, and we'll put it in the next recitation. We'll try to incorporate it.
This one might have been good to flip with last week's recitation.
Okay.
Yeah.
Yeah. Thank you. Yeah. Okay. Yeah.